Hey guys, welcome to Algorithms Conquered. Today we'll be going over the divide and conquer dynamic programming optimization. If you're interested in other dynamic programming optimizations like the convex hull trick, then I've already covered that in a different video, which I linked down below in the description. So I'll be going over the problem subarray squares from the CSES Advanced Techniques problem set. And this problem can also be solved using the convex hull trick. So I'll highly encourage you to check that out if you're interested. Let's get started with the tutorial. So in this problem, we're essentially given an array of n elements and we have to divide it into exactly k subarrays where the cost of making a subarray is the sum of its elements squared. So we need to figure out the minimum cost to divide it into k subarrays such that the sum of the values in the array squared is minimized. And if you see that for this input array, they've cut it this way. So all subarrays need to be contiguous, and every element needs to be part of one subarray. And also keep the constraints in mind. And let's proceed now. So to start with, this has a pretty simple, straightforward dynamic programming solution, which I'm not going to explain too much in detail because the main focus of this video is actually on optimizing it. So simply the recurrence will be, let's say you want to divide the array into k subarrays and you're considering the prefix up to I. So this will be equal to the minimum of k minus 1 j minus 1 plus c of j to I, and j is less than equal to I. So it's basically the cost to divide the array up to j minus 1 into k minus 1 subarrays and the cost of creating a new subarray from j to I. So j is less than equal to I. And our cost function here, as I said, is simply the square of the sum of elements of the subarray. And this is a pretty simple DP solution to it. And the time complexity for it will be O of k times n squared, because we have to divide into k subarrays, and so our states are k times n, and then the transition time for a particular state is n, so it's just k into n squared. And let's actually visualize this once because it will help later on. So this is k minus 1, this is the DP table. And suppose we're considering this cell to be I, then we're saying that the cost to create a subarray from here to some j, and let's say that we want to split it into this subarray. So I'll call this j, this point. And the cost again over here is just j to I. And then what we also need to do is we need to add up this value to it, which is dp of k minus 1 j minus 1. So then we basically get this recurrence, and what I want to define through this is a quantity opt ki. So opt of ki is basically the optimal splitting point. It's this optimal value of j that minimizes this particular expression. And it's not just the optimal value of j, it's the leftmost value of j that minimizes that expression. So what we're doing is for I here, we're looping back through all of these elements, and we're seeing which value of j minimizes that expression, and we're finding the leftmost value of j that minimizes that expression, and we're defining it to be opt of k comma I. So I hope it was easy to see why the transition time is O of n, because for every I, we have to loop back through the entire array and consider splitting it. So we could do this plus this, we could do that plus this, and we can even do this plus this. So we try that for all possible j's, and we finally find this opt k comma I value. So this particular solution, like I said, is O of k times n squared. But what's interesting is, in this particular problem, this value opt k of I is actually greater than equal to opt of k I minus 1. This means that, let me clear this out. This essentially means that suppose we made this division and we found that opt k of I was this j, then it means that for I minus 1, which is basically this, opt k of I minus 1 has to be smaller than or equal to this. It cannot be greater than it. It's just a property because of our cost function in this problem. And I'll be explaining more of that in a bit. So it means that opt of k comma I minus 1 has to be smaller than equal to opt of k comma I, which subsequently means that for any element I plus 1, I plus 2, I plus 3, any element after I, the optimal splitting point has to be greater than or equal to opt of k comma I. So it has to be somewhere here. And this is important because it means that if we can find a way to compute our opt of k comma I in a more efficient manner, we can actually speed up our dynamic programming. Before we do that, I want to talk about the cost function a bit. So the cost function here satisfies something called the quadrangle inequality, which says that the cost from A to C plus the cost from B to D is smaller than equal to the cost from A to D plus the cost from B to C. Visually, this means that if you take the points on a number line, let's call this A, B, C, D, and also this condition is there for this inequality, then this means that the cost from A to C is this, and the cost from B to D is this. Now the cost from A to D is this, and the cost from B to C is this. We're essentially saying that intuitively going wider, making wider subarrays is worse, because we're saying that this split is worse than the red split above. And here we can see that we have a very wide split. And intuitively you can see why that's true, because when you add numbers or when you go higher and then you square a number, then its square increases by a lot more. And if this property holds true, then this also holds true. Now, I won't be going into the proof for this, and I won't be going into how the square of the sum of elements cost function satisfies this property, but I will be linking down this blog in the description below, and it has proofs for a lot of things related to the quadrangle inequality, as well as dynamic programming related proofs. So if you're very interested in the math behind it, you can check it out, but you actually don't really need it, because the simplest way to find out whether the dynamic programming problem can be optimized with this optimization is essentially to run this O of k into n square algorithm, and whenever you should also just store the minimum j. You should also just compute the value of this opt of k comma I, and then you can use checks to And sort you see what you want to do is you want to generate a lot of test cases. You can make large test cases that will comfortably work for this complexity, and you just want to check these values with your program. If you do this for a lot of them and all of them seem to appear monotonic, then you can kind of assume that the cost function satisfies the quadrangle inequality. And also you want to do that instead of mathematically proving it, because it can take a lot of time to prove it mathematically. So till now I've showed you the k into n squared slow solution, and I've given you the dynamic programming recurrence. I've also defined this quantity opt of k comma I, which is the leftmost optimal splitting point. So the leftmost j which minimizes this quantity for a particular I. And I've said that if the cost function satisfies the quadrangle inequality, where wider is worse intuitively, then this inequality for the values of opt also holds. And then I said that if you can find a different order to compute these opts in, then you can speed up your dynamic programming. Now, the order we're currently computing these opt values is basically you check a particular I, and then you check all the values before it. You take an I, and then you check all the values before it. You take an I, and then you check all the values before it. But with this property, we can do something better. And let's look into that right now. And this is where the divide and conquer part actually comes in. So suppose I'm computing dp of k. And I'm saying that this is my entire array. I want to look at its midpoint. Instead of linearly computing dp of k1, dp of k2, dp of k3, I'm going to compute dp of k mid, where L is equal to 1 and R is equal to n, where n is basically the last element, the location of the last element of the array, or the size of the array. So I'm first going to compute dp of k comma mid. And I can do that simply by looping over the left values here, because I'll obviously not loop over the values to the right because I need to split it only to the left. And what happens here is that we know that for any element to the left of this, its splitting point has to be smaller than equal to the splitting point we get for this. So let me draw this out a bit. This is basically the standard divide and conquer structure. And these blue parts are the middle elements, or the midpoints. All right. Because we're doing divide and conquer, I'll also define variables related to the segment length. So let's say that L comma R is the segment, and opt L comma opt R, and this is the range that we will find our j in. We won't look outside of this range to calculate our j, and you'll see what I mean by this in a second. So right, we're computing dp of mid first. As we saw above, the dp value here does not rely on any dp value within the same row. It only relies on a dp value in the previous row. And that means that for this, we can essentially calculate the cost function and take up a value from the last row. And what's interesting here is that the cost function is also easy to calculate and we can do it in constant time using prefix sums. So, and I'm not going to go into that because you should already be familiar with that if you're watching this. You can calculate the cost function in constant time with prefix sums, and you already have the single constant dp value that you calculated for the previous row. So here my optel optar is currently just defined to be from 1 to mid, or 1 to r, because we're considering the whole segment first. And then suppose I find that, let's see, and suppose I find that the optimal splitting point was over here for this particular value. This means that the optimal splitting point for this particular value has to be smaller than or equal to this point, and the optimal splitting point for this value has to be greater than or equal to this point, because again of the inequality we just saw above. So in the first level over here, we see that we do O of n work. Now let's see what happens for the next level. So opt of L will be the same opt of L for this as it is for this, because there were no changes to it, but opt of R changes to this because we know that because of the inequality, this opt value is less than or equal to that opt value. And opt of L for this particular segment will change to the opt value for this. So basically, I'm going to be checking these points for this particular value, and I'm going to be checking these points to calculate the DP for this particular value. And yeah, so you can also see here that the time for computation is O of n. And now let's see what happens in the third level. So we arrived at an optimal splitting point for this value as well. And because of that, we know that the optimal splitting point for the bottom segment over here has to be smaller than or equal to the optimal splitting point for this segment. So let's say that this is the optimal splitting point. This also means that the optimal splitting point for this has to be to the right of that. So essentially the work done will be you iterate over this part for this, and for this you iterate over this part, because you don't need to iterate beyond this element because you can only divide them going to the back. And for this particular segment on the right, let's assume that the optimal splitting point was over here. And that's true because you can see that the optimal splitting point, wait, sorry, it can't be over here. My bad, it can, yes. Yeah, so I was saying that for this, you saw that the optimal splitting point was over here, which means that the optimal splitting point for it has to be to the left of this, or it has to be that. So we got it over here. And the optimal splitting point for this has to be greater than or equal to the optimal splitting point for this one. And so for example, suppose we got it over here. And now, how do we compute the splitting points for these using that information? Well, the optimal splitting point for this segment has to be less than or equal to the optimal splitting point for this segment. Yeah. And if this was the optimal splitting point, it means that we can only check from here. Let me erase this. It means that we can only check from its optimal splitting point, which was here, to the back. And what will the left point be bounded by? Well, we saw that the information we have is basically only from the segments in its parents. So we saw that the optimal splitting point was this. So the opt L for this particular segment becomes this point, and the opt R becomes this point. Because this place is ahead of this place, which means that first of all, the optimal splitting point for this lies ahead of that. And we saw that was here. And then this is between these two. So the optimal splitting point for this has to lie between the optimal splitting point for this and this. And we can see that the segment we cover over here is essentially this. This is also why it's important to have a cost function that can be calculated very quickly, because we Not always will we be allowed to traverse the entire array to calculate them one by one as we would have in the slower DP. But here, if we use prefix sums, we can just calculate the cost from, we can calculate the cost of this segment quite easily in constant time. And so what will be the total work done? We also need to check for this segment. Now, the optimal splitting point has to be to the right of this. So I'm saying that it has to be, um, the optimal splitting point was over here. So it has to be to the right, and it can be anywhere over here. And again, the work here will be O of n, because each value in the array can be accessed at most twice in a particular level. Just because opt of k comma I is less than equal to opt of k I plus 1. And because it's less than and equal to, we can access each splitting point at most twice. And we continue doing this until we basically calculate the optimal splitting point for all values, because we're dividing the array into, we're increasing the amount of segments by 2 each time. We can only do that at most log of n times, and that means that there are at most log of n levels in this. At each level, we saw that the computation time is O of n. So it gives us a total computation time of O of log n for a particular row. And because we have to do this k times, because there are k rows, we have to split it into exactly k subarrays. We get a running time of O of k times n log n, which is substantially faster than our algorithm over here. So if you're still confused, you should either pause the video and go back, or you should try drawing it out yourself, or in fact, even reading this blog over here to understand things better. But let's go over some code and see if we can clear up any doubts you have. So I'm taking input n and k. N is the array length, k is the number of subarrays we need to split it into. Psum is basically my prefix sum array, and I'm saying that the base case is the minimum cost, if we have to split anything into 0 subarrays, is infinity, because we can't make 0 subarrays out of more than 0 elements. So, but we can make 0 subarrays out of 0 elements, and the cost essentially is 0 for that. And now we're going to calculate the DP values using divide and conquer for every row. So let's go over to a divide and conquer function. So I over here is essentially the number of subarrays we want to split into. Ln r is the bounds of the segment, and opt L opt r is our search space. Of course, if L is greater than R, then we can't do anything because we don't have a segment. Otherwise, we find the mid value. Best is essentially the minimum DP value plus the cost, and this is essentially our opt of k comma I, or opt of k comma mid in this case, because mid is the place we find a DP value for. So we loop from opt of L to the minimum of the mid, or the opt of right, because we can't consider DP values that go beyond the point we're actually performing the DP for. This is basically a cost, and you square it to get the actual cost. And then you're saying that best is just the min of the cost of splitting into subarray plus the previous cost incurred. And to keep things simple, I've changed it into DP of I minus 1 to j and plus cost of j plus 1 to I, because you can easily subtract out the prefix sum this way. And again, you're minimizing the leftmost point where you get this optimal value as well. So DP of I mid is best dot first, which is basically the optimal total cost to compute this DP. And then the optimal splitting point is now the second value over here. And then we recurse on the left segment and the right segments. So for the left segment, we use the current optimal L value and the new optimal value. And then for the right segment, we use the new optimal value and then the current optimum right value. And we do this k times. The final answer is just stored at DP of kn. And yeah, that's it for this. So it's possible that some things weren't clear for you because this is a bit hard to understand, and especially I'd say while we do O of N work at each level, but you should draw it out yourself. You can rewatch parts of this video, and if you still don't understand anything, just write down in the comments below. Or in fact, join the Algorithms Conquer Discord server if you aren't already on it. You can ask me questions there about this, and I'll be leaving a link to that in the description below as well. So yeah, I hope you learned something new and enjoyed watching this tutorial. Consider subscribing to the channel to receive updates on videos like these, and also give the video a like. And I'll see you in the next one. Thanks.